Okay, so wanted to finish up our discussion on non-abelian gauge theories, and I mean, you could fill up a whole semester really with the topics, with topics related to non-abelian gauge theories. But I don't have a whole semester. I only have an hour now. So what I have in these notes are, there's a lot of slides. If you go look at it online, there's like 50 something slides, which I probably won't be able to get through all of them. But what I tried to do, so it's kind of a Frankenstein notes. I've kind of put pieces together from old lectures and tried to piece together everything that way. And what I decided to do, since you guys were asking me more about Higgs stuff, I'm not going to talk about QCD so I'm going to talk about how to quantize the non-abelian gauge theory, or at least how to derive the Feynman rules, and then for a general non-abelian gauge theory. And then to apply, QCD is just a specific case of that, really. So all that really changes are the structure constants of your Lie algebra. So I'm not going to talk about that. So I'm going to talk about non-abelian gauge theories, how to quantize them, and then I'm going to talk about spontaneous symmetry breaking. So there's about 5 or 6 slides from the summer that you guys have already seen. On how to spontaneously break a symmetry when you just have scalar fields, and then I'm going to apply it to gauge theories. Okay, so I'm going to couple a gauge theory, first an abelian gauge theory, and then a non-abelian gauge theory to a scalar field, and invoke spontaneous symmetry breaking and see what happens. Okay, so that's our plan. Okay. So last time we learned how to construct theories with non-abelian gauge symmetries, right? So we basically took kind of a top-down approach, right? And imposed the symmetry and then worked our way down to tell us what the theory would look like, what the Lagrangian would look like, type of interactions. Right? And what I want to do now is take that idea of those non-abelian gauge invariants and that Lagrangian that we've written down, and try to extract real interactions. Okay, so in other words, extract the Feynman rules for a non-abelian gauge theory. And then what you can do is you can use those rules exactly like we did in QED. Okay, so you'll see that there's just a couple extra vertices that you have to throw in, because now the gauge bosons interact with themselves. So that can mean that's going to mean that there's going to be more diagrams when you compute a particular process. But it's all the same rules, right? Everything you do is just follow the recipe. Once you have the rules, you just follow the recipe. Like I said, there in general will be more diagrams, but and maybe what you average over might change a little bit depending on the structure of the gauge group that you're using, but it's all the same. Okay. And I put in here, we will interpret and deal with some unphysical degrees of freedom that pop up, but I've decided not to cover that because that's a whole can of worms that we don't really need at tree level. Okay, so these problems arise when you try to quantize the propagator for a non-abelian gauge boson, and so you have to introduce some unphysical degrees of freedom, and these go by the name of Faddeev-Popov ghosts. So GHOSTS, so ghosts. So if you ever hear about ghost particles, know that they're unphysical; they're not real. Okay, so they're much like we learned about Goldstone bosons during the summer, and we know that those aren't physical as well. Right? They can be, unphysical modes can sometimes be absorbed by physical particles, like we'll see today, by the vector particles. but for the most part, they're unphysical, and the only point that they come in is when you go to compute things at the physical, okay? Which I don't think anybody here is going to be doing.
Compute them in what I didn't hear.
Oh, hey, Brownsville, can you mute that? Mute your end. Thanks.
Yep.
Thank you. They only come in when you go to loop level.
Loop.
Yeah, so when you start to compute things where you have loops of, say, gluons or loops of, whatever, you have to also sum over loops of ghosts. Today, pop-up ghosts. Okay. And if you want a good discussion of that, I would look in. I mean, the best discussion of it is in Peskin, because he takes that kind of, not pedestrian, but what's the word I'm looking for? Kind of a working man's approach. You know what I mean? That's not very high level theory. Okay. All right. So what we want to do is first work out the Feynman rules for fermions and gauge bosons in the non-abelian theory. Okay, and we'll take as our Lagrangian the Yang-Mills just general Lagrangian. Okay, so this looks like, if that A superscript wasn't there, you could say, oh, this is QED, right? But the fact that A is there is telling you that you're dealing with a non-abelian gauge theory, okay? Or something with an extended field strength, okay? And the sum, so this is obviously shorthand notation, so you're dotting F mu nu into an F mu nu, and A here, the A index is being summed over using Einstein convention, okay? And so just introducing some vocabulary here. So this Dirac field now, remember we worked out the case where it was a doublet, but you could extend it to be a triplet, quartet, quintet, and it starts to sound like a jazz band, but no, it's you can extend it to be, whatever it would be, depending on your gauge group, okay? And so it would be, in general, they call them multiplets, right? So, and as you can imagine, SO10, these things get monstrous, okay? But you say that these things belong to the irreducible representation of your gauge group G. Okay, I don't want to get into that because again, that Lie algebra and all that stuff is a whole week in itself. Okay, but just know that this fermion transforms in a particular way depending on what your gauge group is. Okay. And the field strength tensor we worked out last time. Remember, it has these two terms that look like QED. But then you have this extra term that depends on the structure constants of whatever your gauge group is. Okay? And finally, the covariant derivative has, again, our coupling that we kind of extracted by hand, our field A, which is kind of like the photon, but now it has this superscript. Right? And that has to be dotted into something, so you introduce basically the generators of your transformation. Okay? So those guys come into play when you calculate certain processes. Okay, so for example, in QCD, these would be what we call color matrices. Okay, so they carry. They're just just typical. They're just some particular matrices. Okay. Okay, so let's work out. So first, work out the propagators. So the nice thing is that the propagators for the fermionic field and the vector gauge boson will be almost identical to what we've had before in the past. Okay. The one difference is that now these things are carrying, this extra charge. Okay, so they have an extra quantum number if you want that you have to account for. Okay, so for example, you'll have the number of fermions in the theory is going to be equal to the dimensionality of the representation. So you have again you have multiplet, so you're going to have multiple fermions. Right? And in general, the propagator, which is this notation here for the fermion, is going to look like this. All right, so you can see that it looks basically the same. So I don't know if we ever wrote it like this, where the K slash is in the denominator. So this is kind of shorthand notation. So what you would do is you would multiply both top and bottom by K slash plus M. Okay, so that would give you the K slash plus M up here. And what you would get in the denominator is K squared minus M squared. Okay. But sometimes you'll see it written like this, where the K slash is in the denominator. So here the alpha and beta are the normal Dirac indices. So those are the guys that get dotted into the gamma matrices, the indices on the gamma matrices. But now we have these new indices, I and J, which are indices of our symmetry group. Okay, and those can run from anywhere from 1 up to the dimensionality of your representation. Okay. So that's the only change in the Dirac propagator. It's just that delta ij, which is saying that you have to conserve whatever the charge is, whether it be color charge or electroweak charge or whatever. Okay? In row 1. An analogy, okay, so this is where things get hairy, okay? When you go to compute the propagator of a non-abelian gauge boson, some things can go awry very quickly, okay? So what we're going to do is we're just going to guess at the form of the vector gauge boson propagator, right? But what you can show is as you go, in perturbation theory, or if you look more closely at the behavior of the theory, you can see that this thing is missing something, okay? And that something has to do with those Faddeev-Popov ghosts that we don't have time to talk about. But for our purposes, the propagator for the vector boson is going to be of the same form. But again, you have to keep track of the color charge. Okay, so remember now our vector bosons carry charge, right, which is denoted by the A or B here. Okay, so you have to keep track of that, all right? And those A and Bs will run from 1 up to the number of generators in your group. Okay. All right, so that's those are the two propagators. Okay, and like guys in Brownsville, I was telling these guys that I'm kind of sweeping under the rug some problems that arise when you try to quantize the propagators for vector gauge bosons in non-abelian theories. But if you want to read about it, it's in Peskin, I think chapter 15, maybe 16, and they go by the topic is Faddeev-Popov ghosts. There he talks about how you fix up the problems that you run into. But for our purposes, this expression that I have here will work for us. Okay. So next we want to try to find the vertices. Okay, and these. What I've done here for the Lagrangian is I've split off the free part. So this was the part. If you go back here, that would come from the QED-like parts from this guy, and the piece that just is the normal derivative here. Okay, so the free theory parts, right? So the parts where that you would get if you set the couplings to 0.
The simple.
Yeah, the simple part. Yeah, the simple part, and then the other parts, the nonlinear terms, is what Peskin calls them. But they're just the interaction terms. Okay, and you can see the first term is our usual kind of fermion boson vertex. Right, so you see the sidebar psi with a gamma matrix in the middle, right, and it's being dotted into our vector field. Right, but remember now our vector field carries the charge A, so we have to include in this Feynman rule what do we call it? I forgot what I called those before. The representation matrices. Okay, these TA matrices, right? Okay, so that's the only complication there. So you can almost straightforwardly write down the interaction between this vector, non-abelian gauge boson and our fermions, it looks a lot like QED except with the introduction of this matrix here. Okay, so that's a good thing. Okay, the tough ones are going to be these guys. Okay, so this guy, which has 3 factors of our vector field. Right? So this is an a cubic interaction, right, between our vector fields. And you notice it's got something that we haven't seen before in a vertex, which is a derivative. Okay? So anytime you see a derivative in an interaction term in a Lagrangian, you should know that this vertex, when you write down the Feynman rule, is going to go like, it's going to have a factor of momentum in it, a 4 momentum. Okay? We'll see that explicitly in a minute. Okay? And then this guy gives me a quartic interaction between the vector gauge bosons. Okay. Okay. So what you want to do when you work out these cubic and quartic interactions is to first write down what your Feynman diagram or Feynman rule looks like, right? And then pick a particular particular convention for the external momentum and the Lorentz and gauge indices. Okay. So for example, what I would do is, so I know it's a cubic interaction. So it's some vertex that has 3 gauge bosons, right, attached to the vertex. Okay. And so what I've done is chosen a convention for the momentum or momenta, where I'm taking all the momenta inwards. Okay. This is just for purposes of easiness. Okay. You could define one of them going out, and you have some minus signs different than what I'll get. Okay. And then I've also chosen a convention for the Lorentz indices, so mu, nu, rho, and the gauge indices, right? A, B, and C. Okay. And just to remind you, I put the form of the vertex on this slide as well, so we can see what to do. Okay. So what we want to do is we're going to have to, we have 3 identical particles coming into this vertex, so we're going to have to sum over all possibilities. Okay, overall possibilities. Okay. So the first thing what we want to do is we want to take one particular contraction. Okay. And so what we do is we take them, so this is just one example, all right? So we take first the gauge particle with momentum k and dot it into, let's see, to the first vector. Oh yeah, so what I'm doing is I'm taking this guy and plugging it in for this thing, right? And then I take the particle of momentum p, this guy, to be the second gauge boson. You guys can see my cursor, right? Okay. And then finally, this guy to be this one, okay? And so what that gives me is this derivative is going to pull down a factor of, because remember our fields go like e to the minus I k dot x, say, right? And so what this thing's going to do, this derivative is going to pull down a factor of minus I k, okay? And so this derivative, it brings down this minus I k kappa, and because the derivative goes like kappa, and it's minus because the momentum, I've defined the momentum to be incoming. Okay, and so what you find is that this vertex with that particular convention gives you this this Feynman rule, basically, right? So you see the minus I coming from, I don't remember where. But it's got the factor of G, it's got the structure constant, right? Here's my factor of minus IK, right? And then I've got some metric tensor coming from these 2 guys, right? All right, so that's one term, right? But like I said, there's 3 identical particles, so in general there's 3 factorial, so there's 6 possible contractions. And each of these are going to alternate signs due to the total antisymmetry of FABC, right? So I can take this expression and just start interchanging things, but I have to keep track of what I'm interchanging because of the anti-symmetry of FABC. Okay. So what it means is that when you sum all these up, you get 6 possible terms. Okay, but you can group them into basically 3 terms. Right. So this vertex is going to go like the coupling G, the structure constant FABC. Right. So what you would get is for each of these terms, you would get F, and then some combination of ABC. It might be CBA or CAB or whatever, but you rearrange those so you can pull that factor out. And that rearranging is going to give you some of these minus signs. Okay. Anyway, so you group them together, and the general structure is a metric tensor times some factor of momentum. Okay, so this is going to complicate things a lot. Okay, so you just imagine, if I'm considering, say, whatever my Dirac particles are. Let's say we're taking 2 gauge bosons, annihilating them into 2 other gauge bosons. All right, so you're going to have 2 of these vertices stuck together, right? And so you're going to have all these terms being contracted on each other. All right, so it gets to be a mess. Okay. Right. So you can start to see why QCD, processes are so hard to calculate. Okay, because you have these gluons that interact with each other, and their vertices, at least the cubic looks like this. The 4 guy, this 4 vertex, from what we just saw, these contractions of the 2 fields together are going to give me metric tensors, right? And then I've got 2 factors of the structure constant. So if I, again, do the same thing, I write down the vertex itself and I choose a convention for my indices, right? So here I don't have any derivatives, so I don't have to worry about defining how the momentum is coming in, right? So there's no derivatives to pull down factors of momentum, so I don't have to keep track of the momentum, okay? So I can write down just a general rule and assign each point a gauge index and a Lorentz index, okay? And then if I, sum over the 4 factorial possible ways, that should give me the Feynman rule. Okay, so again, I have to keep track of, once I write down one term, so this would be one particular contraction, right? Now I would have to do the other 4 factorial minus 1 contractions, right? But I have to keep track of, in doing that, I have to keep track of these, the order of these indices, okay? Because they're going to give me possible minus signs. And it turns out that luckily for us, that out of the 4 factorial ways that you can do the contractions, these things break into sets of 4, okay? And they only leave us with 6 unique terms in the Feynman rule, okay? You guys are supposed to laugh when I say only 6 terms in the Feynman rule. So your Feynman rule looks something like this. So for your quartic interaction, you have basically 3 terms, right? But if you count the terms inside, you get 6 distinct terms, okay? And notice that these things are going like products of structure constants. And I don't know if you can see this, but the structure constants are they have one common index, right? So that, I think it's E that's common between these 2 guys. So they have one index that's being contracted, and A, B, and C, D are open, right? Which agrees with what our diagram looks like. And then there, some combination and some permutations of metric tensors and the indices. Okay, so this is where you would start to, look to do this on the computer. Okay, so if you're asked to compute something that had the 4 gauge boson vertex, and you look at the 4 gauge boson vertex, and you'd say, okay, I'm going to a computer. I'm not going to do this on paper. All right. Even though, if we were to carry on, I would have you do a couple of these just as a rite of passage. Okay. Because I had to do it. Huh?
For my thesis, I did the same for the.
Oh, okay. Okay.
For the paper.
Yeah. Yeah, I did, so for my first project was loop corrections to this vertex, which had been done. My professor just wanted to make me do it.
Just to check his answer.
Well, no, I mean, it had been done a long time ago. Yeah, it had been done probably by some famous people. But that was like the first thing I had to do. And, you know, it took me all summer, but I got it. And I did a lot of it by hand because I just didn't know any better. All right. It's kind of got swept under the rug, or not really mentioned, but it's kind of interesting that our vertices in this theory, so if you go back and you look at the coupling constants, they're all the same coupling constant. Okay? So you see that they all go like G, right? So in general, maybe you wouldn't expect that. You know, you would expect that the three vertex would have some different coupling than the four vertex. Right? But it turns out that it's not a coincidence, okay, that you actually need those coupling constants to be equal. Okay? And you can actually kind of, after the fact, see the need for this equality from the properties of Feynman amplitude. So consider some particular process, right? And you would have some combination of Feynman diagrams that, you know, that would include these vertices. And you would see that, you know, to kill off bad behavior, you need these coupling constants to be equal. Okay? So for cases like QCD, that's been tested, you know, over and over, and that it turns out to be true. Okay? So the coupling constants, they can extract the couplings from different processes and compare and see that numerically they're the same. Okay. Okay, so that's my spiel on quantizing non-abelian gauge theories. Like I said, this is in general. Okay, so you could go off and apply this to whatever gauge group you want, whether it be SU2, SU3, SO10, whatever. And the structure of the rules will be the same. The only difference is that you'll have the structure constants themselves will be different. And the generators.
C, B would be the dimensionality.
Yeah. So depending on they would. So for QCD, you end up finding that these guys, there's 8 of them. So it's SU3, so it's like 3 squared minus. So n squared minus 1, I think, is something. Is the way it goes. Yeah, because in SU2 there's 3. Okay, both. Yeah. Okay. All right. So you know, you could go off and use these general rules, and just know that, you know, the particulars of whatever theory you're working with are kind of hidden in the structure constants and or the vertices. Okay, so what I want to do next is talk about spontaneous symmetry breaking and then eventually the Higgs mechanism. Okay, so the guys here saw these next few slides this summer, but I want to use them to as a refresher because I'm sure you guys all, remember this stuff and have it committed to memory. But I thought, just for my own sake, I'll have a refresher. Okay. All right. So what I wanted to do was look at spontaneous symmetry breaking in a classical field theory. Okay. And so what I have here is a Klein-Gordon type theory. This is a pure scalar theory. Okay. And I've added onto it a quartic interaction, lambda phi to the 4th. Okay. And immediately you look at this thing and you see, it has even powers of the field, right? So that tells me that this thing is invariant under this transformation where I take phi to minus phi. Right? So we would say there's some symmetry, there must be some conserved quantity, blah, 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 right? Forget about this comment with the Gibbs free energy. This was in that lecture that was tying statistical mechanics to QFT. So don't worry about that, okay? All right, so this thing, if you plot it, right, it would look like a parabola, like you plot it in field space, right? The way we have it, okay? But what we want to do is try to change this theory a little bit, okay? And the way we do that is to take this parameter m squared, right? Notice I'm calling that parameter, I'm not calling it a mass term, even though it's m. But I'm going to let this m squared go negative. In other words, I'm going to replace m squared with minus mu squared. Okay? And there's no good reason for doing this. It's just that I can do it, so I'm going to do it. Okay? So I'm going to replace m squared with minus mu squared. So that means that my potential now looks like this, right? And if you actually try to minimize this potential, you see that it has basically two minima now instead of just one, right? Has two non-zero minima, and they occur at this value. Okay? And this value we call the vacuum expectation value of the field phi, right? So the potential looks like this, okay? So before we had something that was just kind of a parabola, or whatever phi to the fourth looks like, or whatever it's called. But it would just have a minima at 0, right? And that type of theory is boring, so we changed our m squared parameter to be negative, and there, now the potential looks something like this, okay? And so what we would want to do is, we want to work, at a minimum, right? And then expand about some minimum, right? So what we have to do is, in order to do that, we have to shift the field, right? We have to take our field and shift it either to the right or to the left so that we get to one of the minimum, right? And then we take whatever that value is and we expand about that point, right? This is just classical mechanics at this point, right? What I'm saying, okay? So let's choose a particular direction, okay? Which I consider the positive one. So I'm going to take my field and I'm going to shift it to the right so that I'm sitting here at this minimum. Okay. So what I need to do is, so I'm shifting the field by the VEF. So I'm rewriting it in terms of this field sigma and the VEF. Okay. And so what I want to do is rewrite the Lagrangian in terms of sigma. Okay. So what I do is I plug this guy into my earlier expression, my original Lagrangian, right, and start expanding everything out. Okay. So the VEF is a constant, so the derivatives aren't going to act on that guy, but they are going to have some consequences, right? So if I square everything out, my theory looks like this, okay? And so what I've done is dropped all the constant terms, so terms that don't depend on the field, right? Terms that would just give us numbers, because all those do is shift, the energy scale either up or down, and we can't measure that. All we can do is measure relative energy levels. So I can drop those terms without worry. And then what I want to do is plug in, to make this a little more compact, I can plug in the expression for the VEF squared, which I have here. All right, so this equation 30. Okay? And what that does is, I see that this linear term in the field sigma, which is kind of worrisome or weird looking, it goes away, right? And the rest of the stuff simplifies a lot. And what I find is my theory looks like this now. Okay, so I started with, remember, I started with a Lagrangian. So it would have been this guy, but I would I'd have a plus mu squared here. Okay, so that would just be, from the point of view of a field theorist, that would just look like a 2-point interaction, okay? Because it doesn't have the correct sign for a mass term. Okay, so we would say that that's some 2-point interaction, and we would have a 4-point interaction. Okay? And that has to do with the stability of the field, of the Lagrangian and stuff. So it has to be, for a mass term, it has to be a minus like it is here originally. Anyways, so we started out with a massless field that had these 2-point interaction and a 4-point interaction. And by minimizing the potential and then shifting our field so that we lie at one of the minima, right? And then we expand out the minima, we end up with a Lagrangian that has, again, a scalar field, right? But now the scalar field has a mass, right? So by going through this process, you basically given the field a mass, right? But now we pick up these cubic and quartic interactions. So we already had a quartic interaction, so we picked up a cubic interaction. Okay? So now it looks like, even though we started out with this symmetry, where if I take phi to minus phi, I have the same thing, that's not, that doesn't necessarily look like what we have here, right? So now if I take sigma to minus sigma, this guy's going to change sign, right? So we don't have, it looks like we don't have that symmetry, right? But actually the symmetry is still there, okay? We say that we've broken it, but really what we've done is hidden it, okay? And just the way that we've broken it is that when we made this choice, okay? So at this point we still had a symmetry, right? But I had to make a choice, either go left or right, right? And when I made that choice, I broke that symmetry because now I'm lying down here, okay? So that's how you can use this idea of, or this process that we've done to break a symmetry or to hide a symmetry. And what it does is, in this case, it gave our scalar field a mass. Okay? Right? And you can do the same thing for theories with in real scalar fields. So now these guys form like a vector, right? And they transform under a particular symmetry, so you can do rotations, right, of the field, and you would find that your theory would be symmetric, right? However, but now what we want to do is take our mass squared term. I think I've already done it. Yeah, here I've already taken the mass squared term and negative, right? So our potential looks something like this, right? This is what we call the Mexican hat potential, or to me it looks more like the bottom of a wine bottle, right? How the wine bottle has that little bump in the bottom. Okay, so this is what it would look like.
I think both have been used.
Yeah.
The Mexican hat and the wine bottle.
Yeah, it depends. I guess it just depends on how high you take the outside. If the outside's lower, then it looks more like a Mexican hat. If it's higher, it looks more like a wine bottle.
Maybe a sweet Mexican.
Sweet Mexican hat.
Yeah.
Ought to stay on though.
But what you find is that, so this is plotted in only a two-dimensional scalar, two-dimensional field space. But you can imagine this being n-dimensional, right? And what you would have is this kind of, this wine bottle type potential, right? So in the beginning, you lie here, right? But this is an unstable point, and so your field would roll down, in particular, what you want to do is minimize the potential, right? So you want to do exactly what we did previously and get down to one of these minima and then expand the field about that point, right? But there's a lot of different choices, right? Here in this case, we could expand along phi 1 or phi 2 or in n-dimensional space, you could pick, the nth, direction to expand in. But the result is the same, right? So when you make this choice of which direction to go, and typically what you do is you choose the last spot in the field vector to make your shift. But the result is the same. So when you make this shift, you end up generating a mass term for your scalar field, at least one of the scalar fields. And what happens is the other directions which you don't do a shift, you still have massless fields. These guys go by the name of Goldstone bosons. Okay? So this theory where you have n scalar fields, right, that has and you've changed this to a minus mu squared, so you have a plus sign here. You minimize the potential. You have to shift to one of the minima to do to expand about that minima. And when you do that, you make a choice and you're breaking the symmetry. Right? You break the symmetries, you generate a mass for your scalar field, and then you have n minus 1 massless fields left over. Okay? And so what you would end up with in this case is a term that looks like this. Okay, so you can see explicitly that you have a kinetic term for these pi fields. Right? There's k of them, you have one massive field, which is our sigma field. And then you've got all types of interactions. So you've got a cubic interaction that just involves the sigma field. You got a sigma field interacting with two pi's, sigma to the fourth, another quartic interaction between two pi's and two sigmas, and then finally a quartic interaction of the pi's. Okay. And again, it looks like because of these cubic interactions that symmetry, that rotational symmetry that we had in this case is gone. Right? It looks like we've broken it. But it's still there. It's just hidden. Okay? And so what you would do is, if you had this theory and you wanted to test it and see if the symmetry, if this thing obeys that symmetry, you go off and try to measure all these coupling factors, these prefactors, right? And from their values, you can kind of reconstruct the original theory, the unbroken theory. And so that's what they're trying to do now at the LHC, which is reconstruct the Higgs theory and see, or reconstruct the Higgs Lagrange, part of the Lagrangian corresponding to Higgs, and see if it is truly, the Higgs mechanism as envisioned by Higgs and what's his face, Weinberg, and the rest of them. I don't do this. This is about Wilson's theorem proving it. But you end up with n-1 massless bosons. Okay. All right. So what I'm going to do now is try to apply this to a gauge theory. So I'm going to try to couple my non-abelian gauge theory to a scalar field theory. All right. And in the scalar field theory, I'm going to have this minus mu squared term. Okay. And I'm going to see what happens. Okay. So we've seen that the gauge symmetry prohibits a mass term from being written down for our vector fields. Okay. So what we can try to do is maybe use this spontaneous symmetry breaking mechanism to generate masses not only for the scalar fields but also for the vector fields. Okay. So that's our goal. Okay, so I had to warn you that these slides are coming from, it's material from Srednicki, and Srednicki uses the weird metric, the minus plus plus plus. Okay, so you'll see some minus sign differences between what you're used to. Okay, and the first example is in this kinetic term. Okay? So, I mean, if you ask me, this is super weird to have a minus sign in front of a kinetic term, but anyways, don't get me started. Okay, I don't go off on my usual east-west metric rant. Anyways, okay, so we're gonna work in. I'm not gonna do it for QED. It's easy enough to just work in what's called scalar QED. So this is a theory where you have your U1 symmetry, so you have your photons, right, and they're coupled to a complex scalar. Right? And a complex scalar you can show carries electric charge. Okay, so so it's just like QED, but instead of fermions, you have scalars. Okay, so it's just a lot easier to work with. All right, and you can generate masses for the fermions using a Yukawa type interaction. I don't know if I'll get to that, but I think it's in here. All right. All right. So our covariant derivative is just the normal QED one. Okay. And I'm going to choose this potential to have a non-zero VEV, right? To have some VEV that's not zero. Okay. And so I'm going to choose a form that looks a little weird compared to what we were doing before. So I've already basically introduced the VEV term here. So this thing would be like, depends on mu over lambda or whatever it is. Okay. So I've got a potential here. It just makes it clear that it's not, has a non-zero VEV. All right. And what I want to do is I want to shift our field by the VEV. Okay. And it turns out, it's not in these slides, is it? It turns out that when you do this, you have some choice. You have some choices, right? You have a freedom in how you shift the VEV. We've already seen it. Right? And so one particular choice which simplifies your life a lot is called a unitary gauge. Okay, so you have different gauge choices you can make as far as the shift goes. So I can shift this field in unitary gauge. In unitary gauge, you write the new field like this. So here's our VEV. This is some new scalar field rho. And up in this exponential is another scalar field called chi. Okay, so I have my two scalar fields here written like this. Okay, and they're real scalar fields. Remember, this is a complex scalar field. These are now real scalar fields. And the nice thing about using this unitary gauge is that when after you shift the potential, or in the potential you have this phi dagger phi term, right? And phi dagger is going to change this into a plus I, and so these exponentials are going to cancel out, and the theory is only going to depend, or the potential is only going to depend on rho. Okay, so that's the nice thing about choosing that particular gauge, the unitary gauge. Okay, so your potential ends up looking like this. Okay, so you have a rho squared term, rho cubed, and rho fourth. Okay, but the interesting stuff is hidden in the covariant derivatives. Okay, so the kinetic term, you can let's see, it doesn't kinetic terms. So what am I saying? These slides are from 4 years ago, so I don't know. The kinetic term provided to the shift. So the theory, theories invariant on local transformations like this, right? Local gauge transformations, and we're free to choose the form of this guy. Right? So what we can do is we can choose this guy to be the same thing that we had in our unitary gauge transformation. Okay, so we can choose this guy to be chi over v, right? And then it'll take the form of what we had back here for the phi field. And so that particular choice determines how what the kinetic term is going to look like. Okay, and we've already seen that when you have phi dagger phi, that exponential piece is going to cancel off, and so this kinetic term with that goddamn minus sign out in front is going to look like this. Okay, so when I plug the stuff in and square it out, I'm going to see that it only depends on rho now, but the rho field now is coupling to our vector field, right? Because the vector field is hidden inside these covariant derivatives. Okay, so I've taken, so this is recap real quick. So I've written down a theory that has a scalar field. So if you imagine setting the coupling to 0, this would be your normal, kind of Klein-Gordon theory with some phi to the fourth or whatever type of phi to the fourth type of interaction. And I've introduced this local gauge invariance, right, or local gauge symmetry. And if we take that top-down approach that we did last time, it would tell us that, we're going to have to introduce some new vector field, right? And that vector field, we could work out its kinetic term, and its kinetic term would look like the normal kinetic term for a photon in terms of the field strength. Okay? But now, what happens is I've got this thing coupled to a scalar field, and the scalar field has this weird, non-zero VEV potential. Okay? All right, so I have to expand the field, right? I have to replace or shift the field, sorry, right? And then I have these covariant derivatives, which are coupling the fields, the new fields rho to the vector fields a mu. Okay? And so what we effectively do is we now have, if you put it all back together, you have a theory that has kinetic term for a photon. Nothing happens to this guy. Right? Here you get a kinetic term for this new scalar field sigma. Right? The potential just becomes whatever it is after you shift it. Right? It's a lot like what we had before. Right? But the interesting stuff is coming from those extra terms in the covariant derivative. Right? Because what you have is, when you put it all back together, you get something that looks like from this term. So when you square this out, it's going to give you a v squared term. And if you take that term with these two guys and the g squared, it's going to have the correct sign for a mass term. Okay? The other terms, the cross term and the rho squared term, are going to give you interaction terms between your vector field and the scalar field. Okay? So what we see is that this vector field now gains a mass, and the mass, because it's a vector field, the mass is going to be mass squared, so it's telling me that the mass has to be g times v. Okay. So what I end up with for this guy, the vector field, is just a kinetic term and a mass term that looks like this. Okay, so even though our local gauge symmetry forbid us from writing down a mass term for our vector gauge boson, we can use this trick of coupling the theory to a scalar theory, and the scalar theory has this weird potential, and then once I minimize the potential shift, do the whole spontaneous symmetry breaking, I find that the scalar field acquires a mass plus some interactions with itself. But through this covariant derivative that I had to introduce because of the local gauge symmetry, the vector bosons also gain a mass. Okay, so this is why they say this is you would look at this if you saw the vector boson had a mass, you say that somehow the symmetry is broken. Right? So this is a simple example of the W and Z have masses, right? But the theory that we have that describes the interactions is a local gauge symmetry. Right? So local gauge transformation, and that would actually forbid masses for the W and Z. Right? So there was kind of a conundrum. Like we want to use these ideas of symmetries and local gauge invariance and all this stuff, but there's a fly in the ointment, and that fly is that these force carriers carry have mass. Okay, and so they had to figure out a way out of that. Okay, and that's where this Higgs mechanism came in. The Higgs mechanism is, or spontaneous symmetry breaking, can give you these masses.
We just suppose that this scalar field, we just suppose that it has interaction with that gauge boson.
Yeah.
And there's no reason for
You just put it in by hand. Yeah, you just put it in by hand. That's one of the detractors of the Higgs theory is that where does the scalar field come from, right? We didn't have the only reason we put it in was to give mass to our vector field, right? And we don't really have a good answer for that yet, right? It just seems to be there. Right? So what you have to do is you work on theories beyond the standard model that predict where the scalar field comes from. Okay, whether it be supersymmetry or some other weird theory. Okay? But those theories because of that scalar field in supersymmetry is a partner to a fermion field. Okay? And so it's natural that scalar field is there within supersymmetry.
even if we justify that it should be there, but the fact that they have an interaction with the gauge boson, it's also another supposition. Right?
Yeah.
So it's not general case that any field has interaction with the other.
What you do is you write down, terms that are allowed by your symmetries.
Yeah.
So once you say, I want to couple, I want to include a scalar field, and I want to couple it to whatever particles, what other stuff I have in the theory, then you use, the symmetries to determine what interaction terms you can write down.
But the vertex would be zero in case that they don't interact with each other.
Yeah, if they didn't interact with each other, we wouldn't know that the scalar field existed because, if matter particles or our force carriers don't interact with it, then we would never know that it was there. Yeah. So you have to include some interactions. Okay.
Okay, so it depends on what kind of theory you're looking at. You say, okay, this theory includes it, this theory does not include it, depending on what you want to.
Yeah, like in QED, we see that the photon's massless, right? And so we can impose this local gauge invariance, and we don't have a problem because it doesn't allow us to write down a mass term anyways, right? So QED was a very successful theory from the beginning, right? But then you move into these cases with the electroweak, or the weak interaction, where you have W's and Z's, and they're very massive. I mean, they're like, almost 100 times more massive than the proton. Right? And so that was, if you think about it, I mean, nowadays we take the W and Z for granted, because they pop up all over the place. And now we have the Higgs, but back in the day, back in the 60s, it would have been really hard to try to figure out how do we incorporate the symmetry stuff, but also have vector bosons that have mass, because that just completely violates the symmetry. It explicitly violates the symmetry. So it was kind of, the standard model itself, that part of the standard model, and the fact that it actually looks like it's that it's true, is really remarkable. I mean, it's just crazy. Okay. So that's why, when they made the announcement, when I stayed up at, it was like 3 or 4 in the morning here, and when they showed that plot, and you see this bump on the diphoton spectrum, I mean, I started crying like a baby, because you just didn't think, I worked on the Higgs my whole, not my whole life, but my whole career, and in the back of my mind, I just thought it would never be discovered. I just thought this is too simple. The theory is too simple. Nature's going to have something, unexpected, and they found it, and now it's they're studying the properties of it, so it's crazy, right? And in fact, I'm not going to get there, but so you can generalize this stuff to non-abelian symmetries. You have to. I'm just going to blow through these really quick, but they're in the Dropbox. Okay. The thing is that now you're going to have more than one vector particle. Okay, so you're going to have to increase the dimensionality of your scalar fields if you want to give masses to all or some of them. Okay. So that's why in the standard model we have the SE2 cross U1, right? So the Higgs thing that you would introduce here, the scalar field, is actually a doublet. It's a complex doublet. So there's 4 degrees of freedom. Okay? And so what happens is 3 of those. So Goldstone's theorem tells you that out of those 4, and you're breaking SU2 down to U1, right? The U1 being electromagnetism. Okay, so you're breaking 3 symmetries. Right? So Goldstone's theorem tells you that you're going to have 3 massless particles, right? 3 unphysical massless particles, and 1 physical massive particle. Okay, but what happens is through this Higgs mechanism, those 3 unphysical states get eaten by the W and Z fields. Okay, so they get incorporated into mass terms for the W and Z. They become the mass terms for W and Z, and that's why they're called. That's why they say that they're eaten. Quotation marks. They don't actually chomp away at them, but they're through this spontaneous symmetry breaking, they get absorbed into mass terms for these vector fields. Okay, and you have one massive scalar field left over, and that's your Higgs boson. Right? And, so that's paraphrasing how this stuff works. Again, it gets more complicated just because you have these generators, right? The generator matrices, which is slightly different notation than what I had in the previous slides, but it's the same thing. And so you can see things get complicated in a hurry, but the basic idea is still there. Okay. And I'm not gonna have time, I'm just gonna stop here, but I wanted to show you guys because I thought that this was funny, that when I first taught this, this was in 2011, so this was before the Higgs was discovered, and actually, so here I'm talking about the Higgs sector, and at that point, they hadn't discovered the Higgs, so all I could show was an exclusion plot. And you can actually see now, so here's 100, 110, 120. So this bump right here, at the time, it looked just like people thought, statistical fluctuation. But this bump right here is actually right at the mass of where the Higgs is. It's about 125, 126 GeV. Okay, but they just couldn't say with enough significance at that point. I mean, this was very early on that this was the Higgs, but it turns out that it was. Okay, but at the time, like I said, if you would have asked me, I probably told them that probably not going to be found, because I just didn't. One of those things it's just hard to believe. But anyways, if you want to work through, I worked through in pretty good detail how you build the standard model and some consequences of it, but guess not. But anyways, so I'll stop there. And if you guys want to go through these, and if you have questions, or, let me know. I'd be happy to sit down and talk, or Skype and talk, or whatever. And let me know if you have questions or problems on the homework other than problem number one. No, I'll take a look at it and see. We guys in Brownsville, before you got here, we were talking about number one, and some discussion. They were asking me if I had any clues, and I told them that I have not worked through that problem yet, so I didn't have any clues. But I'll try to take a look at it, and if I see something that maybe will help, I'll let you know. But what I think what I would do is I would take the expressions that we worked out in the center mass frame and try to boost them to the lab frame. Right?
Well, I mean, we still work in central mass frame there. We just need to take into account that muon mass is infinite, and you will keep being in central in the central mass frame because of infinite mass. But for me, like main part, I got answer. This answer was looking similar because I had like all these signs more or less the same ways. No, actually, I had only denominator, right? But what I did next, I just took general relativity relations between momentum, mass, and energy, and just played with them, and at the end I got the exact answer.
Okay, so you took the center mass frame expressions and took the limit of the mass of the muon goes to infinity, and then just played around with the algebra.
And generally, I just
so that's where the beta
muon equals to mass. Momentum of muon, like vector momentum, equals to 0, and that's it.
Yeah, that's what I was saying the other day, that I think it's just a matter of getting the right expressions, the right algebra. But keep working at it, and let me know. I'll be here. I won't be around tomorrow, but I'll be here on Friday. If you guys want to come by, we can talk. Maybe I'll have looked at it by then. Okay. But just get it to me. You can send it to me next week, early next week. Just enough time that I can check it and give you final grades. Okay? All right. Okay. Well, it's been fun. Hope you learned something.
Yeah.
We rushed through a lot of stuff, but there's a lot of stuff in the Dropbox, so you can always contact me and ask me questions. All right? All right. See you guys.
Thank you. Bye.
See you.
Sticks with the glass.
Yeah.
Or
Maybe,
everything.
yeah, maybe we can take. Would you mind taking a?
Oh, sure.
Yeah.
There you go. Okay, 1, 2, 3. Okay.
Thank you.
We should have had those guys in the background.
Yeah.